Hi and welcome to this tutorial on feature selection. So today we're going to talk about different feature selection methods. So we'll take a look at the variance threshold method. We'll also take a look at a filter method to select the top k best features. Then we'll take a look at a wrapper method called recursive feature elimination. And finally, we'll talk about Boruta. Now, this tutorial is meant to be hands-on, so we will be jumping back and forth between the slides and the code, so that the way it works basically is we're going to explain a certain method, we're going to apply it in Python and see the results for ourselves. But first of all, before we actually jump into the details, we need to know, why do feature selection at all? The first reason is because, well, at equal performance, a simpler model is a better model. So take two models, one of them uses 10 features, the other one uses 5 features, and if both of them have the same performance, then you should really use the model with only 5 features. That is because, it is simpler to maintain, faster to train, less feature engineering, and also less prone to overfitting in the future. So again, faster to train, I already said that. And of course, in many times, you actually improve a model's performance by choosing the right features. So it's not only about making it simpler, you can actually improve your model's performance, and it's always a good idea, right, to do that. And then when to do feature selection. I really think that you should do it before hyperparameter tuning and model selection. The reason being that if you are tuning your model, using all your features, and then you do feature selection, you actually change the feature set, and then you will need to redo your hyperparameter tuning on this new feature set. So really, you're basically wasting time. So this is a step that you should do before choosing your model and actually tuning its parameters. So before we actually jump into the first feature selection method, let's actually go into the code, get ready, get the data ready, set some baseline, explore the data a little bit, and then we'll actually come back to the slides and explore our first method, which is the variance threshold. All right, so we are in Jupyter Notebook to implement everything that we are going to see in the slides in Python. And now again, the goal is just to take a look at the data, get it ready, visualize it, explore it a little bit, and also create a baseline model, which basically is going to be a model that uses all the features, so that later on we can see, does feature selection actually improve the performance. Now, I will not be typing everything from scratch for two reasons. First of all, I really want to put the emphasis on feature selection techniques. So those sections I will be writing with you so that you can see the logic and how we implement it. But the rest, importing libraries, creating visualizations, very basic stuff, train test, split, and all of that is already written here. I'm only going to run it, but still I am going to explain what is happening for you guys. And also that way, less chances of me making mistakes and spending time debugging in front of you. This is nothing that is really interesting. So let's go on ahead and run the first two cells. So again, I'm just importing standard libraries here, pandas, numpy, and matplotlib. And in this case, we are going to use the wine dataset from scikit-learn, which is a dataset where we have multiple features, and then we need to categorize wine in one of 3 categories. And then here, RC params basically is just setting the size of my figures. So let's go ahead and read the data. So again, this is just standard code of how you read data that comes with scikit-learn, and you should get the following. So as you can see, we have a data frame. We have a bunch of different features. We have 13 features to be precise. And then at the end, we have our target, which is basically 0, 1, or 2. So 3 categories of wine. Now here, I decided to have a little bit of fun and make a swarm plot of some of the features of the dataset. A swarm plot is basically a type of plot that shows you the distribution of your data and also, some information about the frequency. So again, using Seaborn here to do the swarm plot, you will get this warning where 8.4% of the points cannot be placed. This is because in a swarm plot, your points cannot overlap. But that's okay, it still gives us a good idea. And you should get the following plot. So as you can see for alcohol, this gives us an idea of the distribution. So as you can see, we see that the data doesn't vary too much, right? Malic acid, same thing, but here alkalinity of ash, we can see here that we have a data that is much more spread out. The other type of information that we can see from this plot is also that we have overlap in the categories, right? So again, taking a look at malic acid here, we can see that we have all three colors here on this row, for example. So that means, that malic acid is definitely not enough to distinguish perfectly between the three categories of wine. So again, this is just a little visualization just to have some fun. I really encourage you to check it out on your own, maybe plot different features, see what it looks like. And then we're going to take a look at the value counts of the target. So again, this is a classification problem. So it is important to see what is the frequency of each of our classes. So we can do this using value counts. And then I'm going to simply plot the same information here, but in a bar plot. And this bar plot, or actually this way of doing bar plots, you're going to see it many, many times throughout this tutorial. So I'm going to explain here what is happening. So X and Y, fairly simple, right? What is your values in X? What is your values in Y that you want to plot? And then, you create your bar plot. I'm always going to write an X label and a Y label to make things beautiful. And then here, this little for loop is how I'm going to add a label on the bar plot. So I am enumerating Y and then getting the index and the value. And then you simply add the value as a string. So this is what it's doing here. So Y is going to be the value plus 1. So you have the actual number sitting on top of the bar. And then you pass in the value, and then you horizontal align it at the center. So let's go ahead and see what this looks like. And you should get the following. So as you can see, we get this nice bar plot, and then we have the value sitting on top of each bar so that it makes it easier to read. So again, we have our categories 59, 71, and 48. So it's not perfectly balanced, right? But it's not it's not really imbalanced that we have to do something like SMOT or etc. So that's okay. We know that we have different frequencies. It's important to know it. So let's go ahead for the train test split. So again, all standard code that I assume that you already know how to split your data set into a training and a test set. So again, you import it from scikit-learn, define your features and define your target. So basically your features is everything but the target column, and your target is only the target column. And then once you do the split, here I am keeping 30% of the data for the test set. I am shuffling it, and I'm also making a stratified split. So when you set stratify to Y, what it's going to do is that it's going to keep the frequency the same between the training set and the test set according to the frequency of our target Y. And again, random state equal to 42, because in this case I am shuffling, and if you want to have the same results as I do, make sure to set the random state to the same number. Perfect. And once this is done, just a quick sanity check. So as you can see, we have 124 examples in the training set and 54 examples in the test set. Now, with all that being done, we are actually ready to make our baseline model, which in this case, we're going to use a gradient boosting classifier that's going to use all the features. So this is going to be our baseline, a classifier that uses all the features, and then we will see, using different feature selection methods, can we select fewer features and still improve the performance of our classifier. So let's go ahead here. So as you can see, I'm already importing gradient boosting classifier, and in this case, we are going to use the F1 score to evaluate our model. So F1 score, really standard measure of performance for classification in this case. So let's go ahead. I'm going to say that first we initialize our classifier, right? So we'll say that GBC is a gradient boosting classifier, like so. And then I will set the max depth equal to 5. This is optional, you don't have to do it. And again, a random state equal to 42. This you have to do if you want to have the same results as I do. And then you once the model is initialized, you basically fit it on your training data. So X train and Y train. And then you are going to make predictions. So I will say that preds is equal to gbc.predict, and then you pass in your X test. And once this is done, you can evaluate your model using the F1 score. So I will say that F1 score all for all features is going to be equal to, we're going to round the value. So F1 score, and then you pass it your Y true, so which in this case it is Y test. You pass in your Y pred, so in this case your predictions, right? So preds. And I want the average of the F1 score to be weighted. This is because, as you saw, our classes do not have the same frequency, so I want the F1 score to be weighted according to the frequency of each class. And we are going to round the value to 3 numbers after the decimal point. And once this is all done, let's actually run this cell. And you should see, so here we have 0.908. So this is our baseline F1 score. So using all the features, we get an F1 score of 0.908. So this is the F1 score to beat, right? So we want an F1 score that is larger, closer to 0. It means that we have a better model. So with all that being done, let's actually go back to the slides and learn about the variance threshold method. All right, so now that we are ready to implement everything, let's first take a look at variance threshold, and then we'll go back into the code and see how we can do it in Python. So the idea behind a variance threshold is super simple, right? So remember, variance is basically a measure of spread from the mean, right? So if your variance is very large, it means that your data is spread out, so far from the mean. And on the other hand, if your variance is very small, so the closer to 0 it is, it means the data is very close to one another and very close to the mean. Now, in the extreme case where your variance is actually equal to 0, it means that you have a feature with a constant value. And if your feature has a constant value, then it is definitely not predictive for your target. So taking the example that we are working with here, which is classifying wine, all right? So suppose that I have a feature that tells me if the wine is a gas, a liquid, or a solid, right? Well, I'm assuming every wine that was tested was a liquid, and so definitely knowing that a wine is liquid is not helping me categorize it, okay? So that's an example, where a feature is constant, its variance is 0, and is definitely not predictive. Now, if you're in a situation where no variance is actually equal to 0, maybe it is very, very small to 0, then in that case you can remove it. And otherwise, if none of the variance is close to 0 or equal to 0, then you can always set a certain threshold, and then you would say, I'm only going to use maybe the top 10 variables that have the greatest variance, or remove the 2 variables that have the smaller variance, etc. So you can always set a threshold and select your features that way. But keep in mind that using the variance is in a way the naive method in a sense, because right, you're only seeing how spread out your data is for that feature. So with all that in mind, let's go back to the code and implement that method. All right, so we're back in the code, and now we're actually going to implement some feature selection techniques, and we start off with variance threshold. So here, as you can see, I'm just making a copy of all my training and test set just to make sure I don't mess up any of the original data. So this is, I think, a good idea to do, just so that we don't have to go back and rerun stuff later on in the notebook. So variance threshold, very simple, right? We simply need to calculate the variance and then decide if one of the variances, is close to 0 or maybe equal to 0, and then we can drop that feature. So let's do it right away. And pandas actually already comes with a variance method. So xtrain v1.var, and then you need to specify axis equal to 0 to get the variance of each feature. And once you do that, you get the following. So as you can see, we have some features with very high variances, sorry. So for example, proline and magnesium, very high variance, right? And then we have other features with much smaller variances. So non-flavonoid phenols is pretty small, same thing for ash. Now, are we ready to make a decision based on that? If you answered yes, actually, you are wrong. Why? Because our features do not have the same scale. And if I just go back here quickly, you can already see here some of the features do not have the same scale. So here malic acid is between 0 and 5, but then alcohol is between 10 and 15. So because our features do not have the same scale, their variance is not comparable at this time. Okay, so you need to make sure that if you are to compare variances, you need to have the same scale for all of your features. So we need to scale our data in this case before making a decision. So from sklearn dot preprocessing, we are going to import min-max scaler. And so by doing a min-max scaling, we are going to force every feature to be between 0 and 1. So of course, we are going to lose some information by doing this, but at this point, the variance becomes comparable, and then we can actually implement the variance threshold method. That is because none of those variances here is actually equal to 0 or, very, very close to 0, like 1 times 10 to the minus 3, So we're going to scale our data here. So I will say that scalar is a min-max scalar. And then I will simply say that scaled xtrain v1, like so, is equal to scalar.fitTransform xtrain v1. Perfect. And once this is done, I'm simply going to plot a bar plot to show the variance of each feature so that it is easier to compare. So like I told you, right? Again, this bar plot comes back. So again, same logic here. So let's just run this cell and you should get the following. So as you can see, we have all of our features here and then we have our bar plot. So let's just zoom out a little bit so you can see everything. So at this point, we need to decide, what features do we drop and what features do we keep? Or you could also say, what is the threshold of the variance that you want to implement for this situation? So again, this is very subjective. And in my case, I am simply going to set the threshold to 0.03. So what does that mean is that ash and magnesium basically get discarded. Those are the two variables that have the lowest variance of all. And then I'm going to keep everything else. So let's zoom back here for the code. So with that decision in mind, I will say that my selected xtrain v1 is equal to xtrain v1 dot drop, and then I'm simply going to say that I want to drop ash and magnesium and specify access is equal to 1, so you are dropping columns. And then of course you need to do the same thing for the xtest, right? So xtest v1 dot drop, like so. Again, ash and magnesium. All right, and of course access is equal to 1. And so once you have selected your features, right? So now we are using only 11 features out of the 13 that are available. We are going to fit the model again. So gbc.fit on my selected xtrain v1 and then ytrain v1, like so. And then we are going to make predictions. So var predictions, so predictions coming from the variance threshold method, is going to be equal to gbc.predict on my filtered xtest v1. Perfect. And then we are going to compute the f1 score. So f1 score var is going to be equal to, again, we're going to round it, f1 score. So your y true, which is ytest v1. You have your predictions, and again, the average is going to be equal to weighted, and you want 3 numbers after the decimal point. And then we can print the f1 score. And I made a little mistake here, so let's see, ytrain v1 is not defined. This is, so as you can see, made a little typo here. So let's just do this. Let's rerun everything just to make sure everything is fine. Perfect. And now this should work. All right. And as you can see, now we get an F1 score of 0.963, which is an improvement, right? So as you can see, we only dropped the 2 variables that had the lowest variance once it was scaled, and already we can see an improvement in performance in the model. So again, just plotting a bar plot just to show that information a bit nicer. So as you can see, now we have our feature selection method. So using all the features, we get an F1 score of 0.908, but selecting using the variance method, so we simply drop the 2 features with the lowest variance, we actually already improved the model's performance and get an F1 score of 0.963. So by using only 11 features in this case. So again, this is very promising, but like I said, variance threshold is pretty much the naive method. Okay, so let's go back into the slides and learn about a filter method now. All right, so now we are back in the slides, and now we are going to take a look at a filter method to select the top K best features. A filter method, really the key here is that you are going to use a measure of importance to select your top K features. And again, here K is a subjective number, right? It could be you want to use the top 3 features, top 5, top 10, etc. But again, the key here is really how do you measure importance? And here you see a little table. It's not an exhaustive table of all the ways that you can measure importance of variables, but it's really important to know, the situation where you're in to select the right criteria. So in our case, we have numerical data and we have a categorical target. So that brings us to the top right panel of this table. And so we will have the choice between either the t-test or the mutual information to calculate the feature importance. And also notice that mutual information is everywhere, right? So no matter the situation you're in, you can use mutual information. So it's usually a safe bet in this case. So actually, for this lesson, we are going to use mutual information. And just quickly, intuitively, what mutual information says is that, how much information do I know about my target by observing this feature right now? So, quickly, this is what mutual information computes. So this method is super simple, right? Basically, what you are going to do is you're going to calculate the importance of all your features, and then you're going to say, you're going to tell the algorithm, well, select the top 3 highest important features, right? So, or then the top 5 or the top 10, etc. So that's it, super simple. So let's go back into the code and implement this in Python. Okay, and now we are back into the code, and now let's actually implement this filter method to select the top K-best features. So again, I am making a copy of my training and test set to work here with K-best features. Now, like I said, there is always this subjective number that you have to decide, how many features you actually want to keep in your model. And in this case, because we are working with a fairly small data set, let's actually run the experiment where we're going to try every possibility, okay? So we'll try, using only the top 1 feature all the way to using all the features, basically, and see, well, which number actually gives us the best performance. Now, again, this is only possible because we are working with a small data set. Maybe you are in a situation where your data set is very large, right? Maybe you have like millions of rows and thousands of features, where in that case, maybe that is not possible and you would have to use something else. And this is why we are actually going to talk about the recursive feature elimination in the next part of this tutorial. But again, for now, let's just stick with this filter method. So we are going to say that from sklearn.featureSelection, let's import select kbest. And now I need to also import my criteria, so my method of measuring feature importance. And as we mentioned earlier, this is going to be the mutual information, so mutual info classif, because in this case, we are doing classification, right? So here I'm going to write a for loop, okay, to try out all the different possibilities, okay? But first I need to have a list of F1 scores to know, what number of feature is actually the best. So an empty list at first, and then for k in range of 1 to 14. So remember, we don't need to start at 0, right? Because using 0 features makes no sense. So we need to start with 1 feature at least. And 14 is excluded. So in this case, it's really ranging from 1 to 13, and we have 13 variables total. So inside the for loop, we are going to initialize our selector, which is select kbest, and then it's going to use the mutual information classif, and then the number of variables k is going to be equal to k. So depending on where you are in the for loop, it's going to take a look at the top 1, top 2, top 3, and so on and so forth. And then you are going to fit your selector. So selector.fit xtrain v2, ytrain v2. Perfect. And then once this is done, you can filter your features. So cell xtrain v2 is going to be equal to the selector.transform xtrain v2. And you do the same thing for the xtest. So selector.transform xtest v2. All right. And then once you have filtered your features, you are going to fit the model on them. So gbc.fit on the selected xtrain v2 and ytrain v2. And then you're going to make predictions. So kbest preds is equal to gbc.predict cell xtest v2. All right. And then once you have your predictions, you can measure the performance of your model. So I will say that f1 score kbest is equal to, again, we are going to round it. So f1 score, and then you pass in your y-true, which is ytest v2, pass in your predictions, which is kbest preds. And again, the average is weighted, and we want 3 numbers after the decimal point. And then you can simply append it to your list. So f1 score list dot append the f1 score kbest. All right. So again, what this for loop is doing, we're going to try every combination, or more every possibility, right? Ranging from using only one feature to using all the features by measuring the importance using mutual classification. So let's run this. And while this is running, this is actually a great time. If you are liking this up until now, if you think this is a good content and you are liking it, maybe drop a like on the video. It's always helpful and makes me feel good as well. So this is done. So now let's take a look, again, making a bar plot to see, depending on what number of features do you select, what is the F1 score that you get. And you get the following figures. So let me zoom out again a little bit. And so you get this. So as you see here, using mutual information, we see that using the top 3 features actually gives us the best performance. It gives us an F1 score of 0.981, which is even better, right, than using the variance threshold method. And even more impressive, I think, is that, here you're using all the features, you get 0.908. That was the performance of the baseline. But using only the top 2 features, you're actually also improving upon the model. And that is really interesting, right? So we went from using 13 features to only 2, and we still get an improvement in the performance. So to me, that is really crazy. It's really impressive. And also notice, no matter if you're using the top 3 variables or the top 7 features, right, you always get the same performance. And this comes back to what I said, at the beginning of this video, right? A simpler model is a better model. So in this case, you should not go with 7, 6, or 5 when you can actually go with 3 features and get the same performance, all right? So that's it for this method. So as you can see, using the top 3 features from mutual information actually gives us an F1 score of 0.981, which is, up until now, the best performance that we've had. Now, if you are curious about, what are the features that were actually selected, of course, there is a way to do that. So the way we do it is we're going to initialize our selector again. So select kbest, mutual info classif, and then here in this case I will say that I want the top 3 because now I know that the top 3 features gives me the best performance, and I will say selector.fit xtrain v2 ytrain v2 again. And now if you want to see what are the selected features, you can actually create a mask. So selected feature mask is equal to selector.get support, like this. So that creates a mask, and then we can filter basically the columns and see what were the features that were kept by this method. So we can say that selected features is equal to xtrain v2.columns, and then you simply apply the mask. So selected feature mask, and then we can display the selected features like so. And as you can see, so the top 3 features that have the basically the highest score of mutual information is flavonoids, color intensity, and proline. So this is how you can really see, what were the features that were selected by your method. So that's it for this filter method. Let's go back to the slides and learn about recursive feature elimination. And now we take a look at a wrapper method called the recursive feature elimination, or RFE for short. Now, with recursive feature elimination, why we call this a wrapper method is because it actually uses the model to compute the importance of a feature. Now, again, it is critical to use a model that can actually compute a feature importance. And most models that can do that are usually tree-based models, so your classic decision tree, random forest, or gradient boosting trees. Those are models that can actually compute feature importance. And in our case, we're using gradient boosting classifier, so it can definitely calculate feature importance here. And the way it works, again, is really simple, right? So take all the features, feed it to the algorithm, and then using the model, right? So using our gradient boosting classifier in this case, we're going to compute the feature importance, and then we are going to remove the weakest variable. And then we are going to check, is my number of features greater than a certain threshold, k? So again, you can tell the algorithm, you know, I want to use only I want to use only 5 features. So it's going to check by removing 1, do I have more than 5 features? If that is the case, it's going to go back and remove the weakest until it actually reaches 5 features. And at this point, the algorithm is done. So again, we still have this subjective threshold, right? Where you need to decide how many variables you want to keep for your model. So with all that in mind, let's again go back into the code and implement RFE. All right, and now we are back into the code and let's implement recursive feature elimination. So as always, I'm making a copy of everything to work with a clean version for this method. And then again, we are basically going to run the same experiment that we did for the filter method. So I am going to implement RFE and then try, you know, what happens when we use only the top 1 feature or using all of the features. But here really what is the difference, right, is that we're not using mutual information to calculate the importance of a feature. Instead, we're using our gradient boosting classifier, right? We're using the model to calculate the importance. So we'll see, you know, is a different way of calculating the importance gonna get me different results. So the way we do this from sklearn, from sklearn.feature selection, let's import RFE. And then again, the same list. So RFE F1 score list. So initialize an empty list. And then for K in range of 1 to 14, then we enter the loop. And then I will say that RFE selector is equal to RFE. Then you need to specify the estimator. So what model do we use to calculate the importance? In this case, it is our gradient boosting classifier. And features to select. So how many features should we keep? So in this case, it's going to be K, right? So we're going to try 1 to 13. And then we can also specify a step, which is really interesting here. So with RFE, you don't have to remove 1 feature at a time. You can actually remove 2 at a time, 5 at a time, 10 at a time, etc. So if you're really working with thousands of features and millions of rows, you know, this is a great way to quickly see, you know, how much can you shrink your feature space, and then, you know, maybe go into more granular experimentations after that. But in this case, again, we are working with a very small data set, so let's just stick with the step of 1. And then RFE selector is going to be equal, actually, we fit it, right? So fit xtrain v3 and ytrain v3. Perfect. And then same logic, so we're gonna filter it. So selected xtrain v3 is going to be equal to RFE selector dot transform xtrain v3. Oops, 1v too much. All right, and then same thing for the tests. So select test v3 is RFE selector dot transform xtest v3. And then once you have selected your features, you can fit the model. So gbc.fit the selected xtrain v3, ytrain v3, and then you can make your predictions. So RFE preds is gbc.predict on the selected xtest v3. All right. And then we are going to compute the F1 score. So F1 score RFE is equal to, you round again, F1 score, pass in your ytest v3. So those are your true labels. Then you pass in your predictions. And again, the average is going to be equal to weighted. And we want 3 numbers after the decimal point. and then we are going to append it to the list. So RFE F1 score list dot append F1 score RFE. All right, so everything should work. Let's run this cell. And again, if you made it all the way here, congratulations. And again, let me remind you, drop a like, maybe subscribe even to the channel. All right, so that took a while to run, but now it is done. And then again, bar plot to just, take a look at the information in a nicer way and see what happened, which number of feature gives us the best performance. And you should get the following. Now, very interesting, right? So what we see is that using the top 3 features actually gives us a perfect classifier, apparently. So on the test set, it achieves an F1 score of 1. So perfect score, cannot go any higher than that. And then we also have 0.981, which is very similar to using the top 3 features, but computed using the mutual information. So really the key here is that, again, top 3 features gives us a perfect classifier, but you can see that numbers are very different, right? So here the top 2 gives us 0.85, whereas with mutual information, we had 0.926. So as you can see, what really is different here in RFE is that it's just a different way of calculating the importance of a feature, right? Here we are using our algorithm, and before we were using mutual information. So the lesson here is that different ways of measuring feature importance will give you different results, right? So really, I think it's important and it's worth it to try different methods to see really which one is going to give you the best results in this case. And so again, we can see which features were selected by the RFE algorithm. So again, I'm not writing this from scratch because it's essentially the same thing as we did before for mutual information. So just reinitializing my selector here, because I know I want to select 3 features and I have 13. I actually made a step of 10, so that it's only going to run once. Fit the selector, and then you get your mask with the same method, get support, and then you can filter on your columns. And then you should see here that now we have color intensity. We have this feature right here, and we also have proline. So as you can see, different features were selected in this case, because again, a different way of measuring the importance, and we also got a different result. So that's it for RFE. So now let's go back to the slides to learn about the last method that we will cover in this lesson. And now we reach the point of Boruta, and with Boruta, it gets interesting because we take the human out of the equation. So up until now, variance threshold, using a filter method, and even using the recursive feature elimination always required us to set our own threshold, right? We had to decide, of a threshold for the variance, or we had to decide, how many variables should I keep? Do I want to keep 3, 5, 10, etc. Now with Boruta, we don't need to do that anymore. This is a way of like an automated feature selection algorithm where we actually don't need to say, how many variables we want to keep. And the way it works is really impressive, I think. So basically, Boruta starts by creating shadow features, and those are randomly shuffled versions of each of your feature. And then it's going to compute the importance of each shadow feature using your model, by the way. So in a sense, this is also a bit of a wrapper method, right? Because it uses the model to compute the importance. So going back, sorry, I diverged a little bit. So it's going to compute the importance of each shadow feature, and then the highest score of the shadow feature becomes our threshold. And then it's going to take a look, is the importance of the original feature higher than this threshold? If that is the case, the algorithm decides to keep it. Otherwise, Boruta decides to discard it. Now, this is a bit hard to understand, just with text. So let's just illustrate it with a quick example. So suppose that we have this data set here. We have 3 features, okay? And we're going to run through Boruta. So first step, create shadow features, okay? So as you can see, shadow 1 is a shuffled version of feature 1, shadow 2 a shuffled version of feature 2, and shadow 3 a shuffled version of feature 3. Now, once this is done, Boruta is going to calculate the importance of each feature using your model. So here, as you can see, we have the importance of each of our features, and then we take a look at only the importance of the shadow features and find the highest one. So in this case, shadow 2 got the highest importance. It has a score of 10. And now we are going to take a look at each of the original feature and see is the importance greater than 10 or not. So in this case, feature 1 with an importance of 4 is lower than our threshold, so Boruta decides to discard feature 1. But for the case of feature 2 and feature 3, both of their importance is higher than 10, higher than the threshold, and so Boruta decides to keep those features. Now, of course, running this only once is not enough, right? What happens if when you randomly shuffle them, the feature actually doesn't get shuffled? Or how about, it was shuffled in such a way that the importance was really low, but if you shuffle it some other way, the importance changes. So running it once is not enough, right? Because of this randomness. So that's the cool thing with Boruta. You're going to run it multiple times, and then it's going to create a distribution of features either to keep, to drop, or you're not really sure what to do with them, okay? So it makes pretty much a binomial distribution. So here in this figure, you actually see an example where we run it 20 times. I think the default in the algorithm, you actually run it 100 times. And so you would see that, if in your 20 trials, a feature gets selected most of the times, right? Then it becomes placed at the right of the distribution here, so it becomes a feature to keep. And if most of the time your feature gets discarded, then it becomes a feature to drop. And then you have this gray area where sometimes the feature is discarded, sometimes the feature is kept. So those are what we call weak features, okay? And so you could run basically two experiments where you run a model with only the feature that Boruta is sure that you have to keep, and then using the features that Boruta is sure and also the weak features, and see how that affects the performance of your model. So with all that in mind, let's again go back into the code and actually implement Boruta for ourselves. Okay, and we are back into the code to implement Boruta, which is the last method that we will cover today. So again, making a copy of everything. And like I said, Boruta, we don't need to specify anything. Boruta is going to do the work for us. We don't have this subjective threshold to set anymore. So very, very cool, very exciting. So the way we do it is, of course, you need to install Boruta. So assuming that you have done that, you can do it in Anaconda, by the way. So from Boruta, let's import Boruta py, like so. And then same thing, right? So Boruta selector, so initialize the selector, is going to be equal to Boruta py, and then pass in your model and also the random state, because like I said, you are randomly shuffling your data. So to make the experiment reproducible, you need to set a random state. And then once this is done, we say that Boruta selector.fit. And in this case, Boruta doesn't work with data frames, unlike the algorithms from scikit-learn. So you actually need to pass it the arrays. So xtrain v4.values here, and then ytrain v4.values.rattle, like so. All right. And then once it is fitted, you're going to filter. So selected xtrain v4 is going to be equal to Boruta selector.transform on xtrain v4. All right. And then you do the same thing for xtest. So xtest v4 is Boruta selector.transform xtest v4. Perfect. And then once this is done, we are going to fit the model on the selected features. So gbc.fit on the selected xtrain v4, ytrain v4, and then you can get the predictions. So Boruta predictions is equal to gbc.predict on the filtered xtest v4, and then you compute the F1 score. So Boruta F1 score, like so, is equal to round F1 score, pass in your true label, which is ytrain v4, you pass it the predictions, so Boruta preds, and again the average here is going to be equal to weighted, and again 3 numbers after the decimal point. So again, this is going to take a little while to run, so if you haven't done so, again, show me that you like this video, drop a like, drop a comment, and even subscribe to the channel. Always helps me and really encourages me to keep doing videos if you are enjoying them. And I made a little mistake here. Again, we have to pass it the values, so the arrays in this case. So sorry about that. Let's rerun this cell, and I'll be back once it is done running. All right, and now that this is done running, we can again take a look at the selected features. So the way we do this is the same as before. So we're going to create a mask. So selected features mask is equal to Boruta selector dot support, like so. And then again, filter on your columns and take a look at the selected features. So in this case, we have 9 features that were automatically selected by Boruta, and you can see which one were chosen. Perfect. And now let's take a look at, from all the methods, which one gave us the best performance. So this is what this bar plot is doing right here. And you should get the following figure. So as you can see, we have our filter selection, feature selection methods, right? So we used all the features, variance threshold, where we selected 11 of them. We filtered using the mutual information, picking up the top 3 features. We used the recursive feature elimination method that also gave us that the top 3 features give the best performance. And then we have Boruta, which automatically selected 9 features for us. And as you can see, well, all feature selection methods gave us a better performance than using all the features. Boruta, by the way, with 9 features gives us a 0.982, sorry, which is better than variance threshold, slightly better than using mutual information. But in this case, RFE is really the champion method in this case. But again, Boruta is super interesting because we did not have to run any experiments, right? We don't have to run for loops to see which number of variables is optimal, right? So for something that was completely automatic without the human inside the equation, this is really a really good performance, right? All right, so that's it. This is how we implement every feature selection method in Python. And that's it for this video. I hope that you enjoyed it and that you learned something new, and I'll see you in the next one.